Welcome to Lesson 11-1. Today we are introducing machine learning as a practical extension of the computational tools you have already learned. We will focus on supervised learning and linear regression, emphasizing how to evaluate and interpret these models in a physics context. By the end of this lecture, you should understand machine learning as data-driven modeling. You will learn key terminology, implement a basic workflow using scikit-learn, and critically evaluate regression coefficients and errors to ensure your models are physically meaningful. Machine learning is incredibly useful in physics and scientific computing because we frequently deal with large amounts of experimental or simulated data. For instance, we might need to find calibration curves or create fast approximations for expensive simulations. Supervised learning helps us extract relationships from these examples. Let us define some core terminology. A feature is an input variable, usually stored as an array X, while a target is the output we want to predict, stored as Y. In regression tasks, we predict a numerical value, and we always evaluate how well our model generalizes to unseen test data. We will use standard Python scientific libraries for this work. Alongside NumPy, Pandas, and Matplotlib, we are introducing scikit-learn. This library provides robust tools for building machine learning models, splitting data, and evaluating performance. Here, we complete our library imports. We also initialize a random number generator with a fixed seed. This ensures that the synthetic noise we add to our data later will be exactly the same every time we run the notebook. The output confirms that our libraries have imported successfully, meaning our Python environment is ready for the machine learning workflow. A standard supervised learning workflow follows a logical sequence. We start by preparing our data, selecting meaningful features, and splitting the data into training and testing sets. We then train a model, make predictions, evaluate the error, and finally interpret the results visually and physically. Let us apply this workflow to a familiar physics problem: spring calibration. According to Hooke's law, the force is proportional to the extension. We will use a linear regression model to learn the spring constant from synthetic experimental data that includes some measurement noise. In this code block, we generate our synthetic data set. We define a true spring constant of 12 newtons per meter and add a small systematic offset. We then create 40 sample points for extension and calculate the corresponding force, adding random Gaussian noise to simulate experimental error. Our synthetic data is stored in a Pandas data frame. Looking at the first few rows, we can see the feature column for extension in meters and our target column containing the noisy force measurements in newtons. Before training any model, we should visualize our raw data. This block of code uses Matplotlib to create a scatter plot of the force versus the extension. Visual inspection is a crucial step to ensure the data is sensible. The plot shows a clear upward trend, as expected from Hooke's law. However, the points do not lie on a perfectly straight line because of the synthetic measurement noise. Our goal is to find the best fit line through this noisy data. Next, we isolate our features and targets. Notice that scikit-learn expects the feature matrix X to be two-dimensional, so we use double square brackets to extract the extension column. The target vector's sta is extracted as a standard one-dimensional series. Printing the shapes confirms we have 40 samples. Our feature matrix X is 40 by 1, while our target vector Y has 40 elements. The data structure is now correct for scikit-learn. We must not evaluate our model on the exact same data used for training. Here, we use the train_test_split function from scikit-learn to randomly set aside 25% of our data as an unseen test set. The output shows our split was successful. We now have 30 samples dedicated to training the regression model, and 10 samples held back purely for testing its predictive accuracy. Now we instantiate and train the model. We create a linear regression object and call the fit method using our training data. After training, we use the predict method to estimate forces for our test set, and we extract the learned intercept and slope coefficients. The model estimates a spring constant of 12.04 newtons per meter, which is very close to our true underlying value of 12. It also captured the small, systematic intercept, showing that the model successfully learned the physical relationship despite the noise. To visually verify the model, we generate a smooth line over our extension range. We create an array of extension values, ask our trained model to predict the force along that line, and then prepare a plot comparing the model's prediction against both training and test points. The resulting plot shows our linear regression prediction as a solid line. It nicely bisects the noisy training points, shown in blue, and aligns well with the unseen test points, shown in orange. The model has captured the general trend without tracking individual noise fluctuations. While visual checks are great, we also need quantitative metrics. We calculate the mean absolute error and the root mean squared error to measure how far our predictions deviate from true values in newtons. We also compute the R-squared score to see the proportion of variance explained. This code gathers our calculated metrics and formats them into a clean pandas data frame so we can review the numerical evaluation of our model on the test set. The output shows a mean absolute error of about 0.14 newtons and an R-squared of over 0.98. These indicate a strong fit. Remember, these error values must always be interpreted relative to the scale of your experiment. We can also look at individual predictions. Here we build a data frame that lines up the true force from our test set against the predicted force. We then compute the error, or residual, for each specific test point. Looking at the table, we can see exactly where the model overpredicted or underpredicted. For instance, the first entry has an error of about half a newton, while others are off by just a few hundredths. A powerful diagnostic tool is a residual plot. The residual is simply the predicted value minus the measured value. If our linear model is appropriate, the residuals should be randomly scattered around 0, with no clear systematic pattern. This code sets up that scatter plot. We finish configuring our residual plot by adding a legend, a grid, and displaying the figure. The residual plot confirms our model is behaving well. The errors are scattered above and below the 0 line without forming a distinct curve. If we saw a clear U shape here, it would indicate that a simple straight line is missing some underlying physics. Scientific interpretation is key. Our model is useful because its slope gives us the spring constant. Always ask yourself if the sign is correct, if the magnitude is physically plausible, and if the prediction holds up on unseen test data. Linear regression can handle curves if we engineer our features correctly. Consider uniformly accelerated motion. The position depends on time and time squared. We can supply both time and time squared as separate features to let the linear model learn initial velocity and acceleration. We create a new data frame for this motion data. Notice how we explicitly calculate time squared and store it as a second feature column. This is a simple but powerful example of physics-informed feature engineering. Our data frame now contains time squared, and the noisy position data. By expanding our feature space, the model can now perform a multiple linear regression to fit the parabolic trajectory. We split this new motion dataset and train another linear regression model. We pass in both time and time squared as our feature matrix. After fitting, we generate predictions for the test set. We print out the model's coefficients. The intercept corresponds to the initial position, the first coefficient to the initial velocity, and the second coefficient is half the acceleration, according to the kinematic equation. The output is very encouraging. The estimated acceleration is 1.175 meters per second squared, compared to the true value of 1.2. The initial position and velocity are also recovered accurately despite the noise. Let us visualize this fit. We create a dense array of time values, compute the corresponding squared times, and ask the model to predict the position. We then plot this smooth prediction curve over our noisy scatter data. The plot shows an excellent fit. Even though we used a linear regression model, Providing time squared as a feature allowed it to perfectly map the parabolic curve of accelerated motion. We compute the same evaluation metrics for the motion model. We compare the model's predictions on the test set against the true measured positions, checking the MAE, RMSE, and R-squared values. The output shows an RMSE of about 0.9 meters, which is consistent with the standard deviation of the noise we added to the synthetic data. The high R-squared confirms the model explains almost all the variance. What if we do not provide the right features? If we only provide time to our model and ignore time squared, the model is forced to fit a straight line to curved data. We set up a new model with this limited feature to demonstrate this issue. We compare the error of this overly simple model against our full physics-informed model. We print out the root mean squared error for both to see the quantitative impact of missing the acceleration term. The output tells the story clearly. The simple model has an error of 3.3 meters, while the proper model has an error of 0.9 meters. A poor choice of features drastically hurts performance. To truly understand the impact, we plot both models together. We generate predictions for the simple straight-line model and plot it alongside our parabolic model for a clear visual comparison. This plot perfectly illustrates underfitting. The straight line, in solid blue, entirely misses the curvature of the actual motion. The model was mathematically successful at fitting a line, but physically inadequate because it lacked the time-squared feature. For guided practice, try adjusting the parameters in this notebook. Change the noise levels, alter the train test split, or experiment with adding unnecessary features like time cubed to see how the metrics and interpretations shift. To summarize, machine learning is a powerful data-driven tool, but it requires scientific reasoning. Feature engineering allows linear models to capture complex physics. In Part 2, we will build on this by moving from regression tasks to classification tasks.